Everyone knows rock, paper, scissors, unless you have been living under a rock. Well, bad idea. Someone might destroy a house with a piece of paper. But here's the weird thing. Despite how simple this game looks, it hides structure that shows up in algorithms, AI, and real systems. We all memorize the same rule. Rock beats scissors, scissors beats paper, and paper beats rock. End of story. Except, this rule doesn't explain why the game behaves the way it does. So why is there no best move? Why does predicting your opponent help, but only sometimes? And why does adding one extra option completely change the game? To answer that, we need to stop thinking in symbols and start thinking in structure. Forget hands, forget rocks and paper. Think of rock, paper, scissors as a graph. Each move is a node, and an arrow or edge means beats. Suddenly this isn't a hand game anymore, it's a directed cycle. Now watch what happens. We can rotate the graph, same game. We can change the symbols, same game. We can even reverse the arrows, still the same structure, just mirrored. The labels don't really matter here. The arrows do. This is the first hint at the true power of thinking in structure. In this graph, every move wins exactly once and loses exactly once. There's no dominant node. But that's not an accident. It's precisely what balance looks like. So what's the best strategy? Counterintuitively, randomness. If you pick each move with equal probability, no opponent can exploit you. To illustrate that, we simulate 10,000 repetitions of rock, paper, scissors. First, uniformly random versus uniformly random. Wins, losses, draws, perfectly balanced. Even the number of consecutive draws drops off exponentially. Fairness isn't just a feeling here, it's measurable. But bias changes everything. If one player favors a move even slightly, an adaptive opponent can learn simply by keeping count of your moves and punish it accordingly. Predictability loses. This is why randomness isn't chaos, it's protection. Now let's break the game carefully. Add Lizard and Spock. The game still works because it stays balanced. Every move wins exactly twice and loses exactly twice. How do you think the simulation results change for this game? The number of draws is simply cut in half, at least for a reasonably random move selection. We could generalize rock, paper, scissors to any odd number of moves. However, the moment symmetry breaks, which is always the case for an even number of nodes, strategy collapses into dominance. So far, we've been looking at rock, paper, scissors or its extensions as a relationship between moves. But there's another way to look at the exact same game, as a process. Here's the entire game logic of rock, paper, scissors written as a rule. If both players pick the same move, it's a draw. And if it's a draw, you play again. That's it. Now watch what happens when we illustrate this process as a graph. This loop is the draw. Every time both players match, the game literally calls itself again. That's why draw streaks exist, because the structure allows them. And here's the interesting part. The cycle graph we showed earlier describes who beats whom. This call graph describes how the game unfolds over time. Same game, two graphs, different questions answered. Let's say we're building a very simple AI to play rock, paper, scissors. At first, it plays randomly because it knows nothing. But over time, it starts counting what the opponent actually does. Now it faces a choice. If it always plays the best counter, it can easily be exploited. If it just plays uniformly random, it wastes information. So instead, it biases its randomness. This is exploitation versus exploration. Use what you've learned, but never commit so hard that you become predictable. More advanced systems formalize this with math, but the intuition is the same. Pokémon starts exactly where rock, paper, scissors ends. Now we have super effective and not very effective moves instead of just winning and losing. The full type system is more complex and also includes neutrality and immunity. This type chart is a graph, just written as a matrix. And unlike rock, paper, scissors, it's not symmetric. But Pokémon isn't trying to be mathematically balanced in this sense. It's trying to be playably fair. There are many things to consider. So here's the real question. Do you think Pokémon is balanced? Or is it intentionally unfair in a way that creates strategy? The Yu-Gi-Oh! Games, the Sacred Cards and its evil sibling, Recursive of Destruction, use an attribute system that brings back explicit beats relationships, just like rock, paper, scissors. But they also allow neutral matchups, which are the missing relationships in the graph. So not every fight is about attributes, sometimes only monster stats matter. This makes the graph sparser and strategy more contextual. Now, is this system balanced? Or does it trade balance for clarity? Rock, paper, scissors teaches us something fundamental. When no option is strictly better, structure decides outcomes, not intuition. And this is just the beginning, because the moment games add movement, memory or constraints, graphs stop being simple cycles and start becoming puzzles, literally. Rock, paper, scissors isn't deep because it's complicated. It's deep because it's structured. Once you learn to see the structure, you start seeing it everywhere.